Hello, everybody. Welcome to today's grand seminar and happy Black Friday. Today we have one speaker, one talk. Our speaker is AmirMahdi Jafary. He will be giving a talk on transport embedded neural architecture, redefining the landscape of physics over neural models in fluid mechanics. AmirMahdi Jafary is completing his master's study with a focus on biomems, bioengineering, and computational fluid dynamics at Sharif University. He has recently concentrated on research involving physics-informed neural networks with a particular focus on addressing their limitations in solving convection diffusion equations, a complex class of partial differential equations commonly encountered in fluid mechanics. His goal is to improve the training techniques for neural networks to better handle these challenging problems. With that short introduction, the floor is yours, Amir, and you can start your presentation.
Yes, thank you very much for the introduction, and I appreciate the opportunity to speak today. My presentation focuses on the applications of physics-informed neural networks and their potential to advance our understanding and modeling of transport phenomena in fluid dynamics. And so, Uh, let's begin by exploring why transport equations play such a critical role in biotechnology. These equations help us understand and model how a scalar quantity, such as heat or concentration, is distributed across a domain, and the distribution is governed by three key mechanisms. The first one being convection, where a quantity is transported by the flow of medium, for example, a fluid like blood or air. And the second mechanism is diffusion, which occurs at the molecular level. And the random motions of molecules are driven by molecular collisions. And the last one is reaction, where the quantity of the substance changes due to chemical interactions. The first example I brought is cancer treatment through targeted heating of tumors. In certain types of cancer treatments, a specific tumor is heated to destroy cancer cells, and infrared radiation is applied to the skin, and then the radiation penetrates the tissue to reach the tumor beneath. And once the tumor is heated to a certain degree, the cancer cells are killed. And understanding how heat from radiation of infrared is transported in the body is important for this process, and transport equations allow us to model the temperature distribution within the tumor and the surrounding tissue. The next example involves drug absorption and delivery of drug in the bloodstream. When a drug is introduced into the body, whether by injection or digestion, it must travel through the bloodstream to reach its target. And along the way, it often undergoes chemical reactions to neutralize pathogens which are causing the illness. And for another instance in the image, we can see the concentration of a constant agent, which is commonly used in MRI scans. And it highlights how the drug spreads through the blood vessels and interacts with the tissues along the way. And the third example, and the one I'll be focusing on in my presentation, involves surface-based biosensors for detection of biomarkers. And these biosensors are used in point-of-care devices to detect biomarkers and biomolecules in biological samples such as blood, urine, or saliva. And in this method, a sensor is placed on the bottom of the channel, and then channel is filled with the biosample, and the detectors, which are immobilized and fixed on the surface of the sensor, will capture the molecules, and a signal will be transferred, and the concentration of that certain biomarker will be um, calculated. So In order for simulation of biosensors, we need to understand their governing equations. Um, the schematics I've brought here represents a microchannel that is filled with a fluid sample containing biomarkers, and on the surface of the sensor, which is shown here with greenish color, detectors are immobilized, and as the channel is filled with the fluid, the detectors interact with biomolecules, which triggers a reaction, and the reaction generates a signal that can be measured and enables us to detect the concentration of that biomarker. To simulate this behavior, we need to address two key aspects. The first aspect are the hydrodynamic parameters, such as velocity and pressure of the fluid within the channel, and to ensure that biomarkers are delivered efficiently to the sensor surface. And the second one is the concentration of species, which here are the biomarkers, and it involves understanding how biomarkers are transported to the surface of the sensor through convection and diffusion, and how they interact with the sensor through surface reactions. And both of these aspects are modeled using partial differential equations, which describe the transport phenomena occurring in the microchannel, and can be solved with several numerical methods, such as finite element method. And however, there's another approach which I'm so much interested in, and that is physics-informed neural models, because they have several advantages over classical methods, such as a finite element method, because they can integrate experimental data, and along with integrating governing physical equations and physical laws into their frameworks, and they can avoid the challenges associated with mesh generation, which many of the classical methods, such as finite volume or finite element, sometimes encounter. And they are more versatile and capable of incorporating data from anywhere within the domain, while classical methods rely heavily on only boundary conditions and initial conditions. So to better understand how PINNs address hydrodynamic parameters, I've listed some of the familiar equations which are typically encountered in such problems, and along with their corresponding loss functions. The first equation is boundary condition. They describe the constraints at the edge of the domain, such as the velocity at the wall or concentration of the species at the surface. And in the context of PINs, boundary conditions are expressed as norm-like loss functions, and they quantify the deviation between the boundary values predicted by the neural network and the actual values specified by the problem. And similarly, initial conditions, which describe the state of the system at the starting time, are treated in the same way, and they are both effectively serve as the input data set for the PIN. And the next one is incompressibility, which is a crucial requirement, stating that the divergence of the velocity field must be equal to zero in compressible flows. And finally, the most important constraint is the Navier-Stokes equation, which govern all types of fluid flow and must be satisfied in every scenario. And as shown below, the total loss is a weighted sum of all these individual loss terms, the boundary condition and the boundary condition loss, which ensures the network respects the boundary constraint, the initial condition loss, which aligns predictions with the starting condition, and the physical constraints losses like incompressibility and Navier-Stokes. And by combining these terms, the total loss captures all of the key aspects of the hydrodynamic problem. And during training, this total loss is minimized using backward propagation, which updates the weights of the neural network to improve the accuracy. But for transport equations, the optimization procedure is not similar to hydrodynamics. Since to start with, we need to calculate the loss from the transport equation PD and add it to the total loss function, as we discussed in the previous slide. And in theory, this seems pretty straightforward, but in practice, transport equations might introduce optimization challenges that can make finding the global minima uh, and the physical solution of the problem extremely difficult. So when transport equations are incorporated into the total loss function, the resulting loss landscape often contains numerous false minima. In the first example that I've brought is a type of false minima which is often encountered in solving convection diffusion problems using PINNs. And the result I've shown is an investigation of the behavior of 1D convection diffusion equation in a periodic domain. The correct solution, as is shown on the left heat map, is a wavy sinusoidal pattern over time. And those familiar with the analytical solution of such problems via such as separation of variables will recognize this sinusoidal nature as expected. However, PINN solution illustrated in the right heat map reports a constant value of 1 shortly after the initial period. And however, although this result clearly deviates from the true behavior of the system, it is still mathematically correct. And aside from the brief initial period where initial conditions are correctly satisfied, the solution for later times converges to a constant value of 1. And this outcome is unphysical. However, it does respect the convection diffusion PD. And the next example is a study on optimal transport, which are closely related to the continuity equation in fluid mechanics. And the correct solution, which is computed using finite element, is shown in the figure, and it illustrates how probability density evolves over time across domain. And in contrast, the PINN solution is shown below, which shows that the network remains stuck at the initial condition and fails to capture the time evolution. So this solution is mathematically correct, but it's not physically correct, and shows that sometimes when encountering with convection diffusion problems, PINNs struggle to find the physical solution and get stuck into the trivial, pseudo-trivial, or static solutions. Let's review a couple of proposed methods which have been addressed in related studies. One method is to use sequence-to-sequence learning, and this approach divides the whole time span into smaller time steps, uh, which is similar to the methodology of classical methods such as a finite element, and starts with the first time step and is trained with the output from first time step serving as the initial condition for the next. And the process continues sequentially until the entire time span is covered. The second method, which is curriculum learning, is similar to the previous method, and instead of dividing the time span into smaller steps, it begins by training the model on simpler versions of transport equation using coefficients that model can easily learn. And then gradually these coefficients are adjusted incrementally toward the desired value. and which allows the network to adapt progressively and overcome the difficulties in training on the more challenging coefficients. Um, Another approach is to use the stream function formulation, which has been used in many studies when trying to solve hydrodynamics problem, which eliminates the need to explicitly include the incompressibility loss in the total loss function, since the stream function by definition uh, satisfies the divergence-free constraint. So it ensures incompressibility through the stream function representation. And the final method is to introduce a penalty term, which is designed to um, increase the loss function when the model encounters undesirable scenarios during training, and helps guide the model away from these situations and improves its overall performance. So, since none of these approaches I discussed was helpful for our experiment, which I'll be discussing later, and to overcome the optimization challenges, I proposed a novel approach to mathematically embed transport equation into the framework of the neural network. So the idea is to ensure that regardless of the weights of the neural network, its output will always satisfy the transport equation. And by doing so, we eliminate the need for the network to learn the transport equation explicitly as part of the total loss function, and simplifies the learning process. So the pipeline for the proposed approach is that in the first step, we construct and initialize a neural network. And then at the stage, the network produces an intermediate output that is unconstrained and does not yet satisfy the transport equation. Then we generate a constraint output by mathematically transforming that intermediate output. So the resulting output vector would always satisfy the transport equation. And then we train the constraint output and update the weights of the backbone neural network.
Sorry, can you explain what you mean? Or are you going to explain what
Yes.
you mean? Because it's not clear.
Yes. I will explain the embedding block in details in the
Okay,
next slide.
right. So in the
Yes.
step one, you only
Yes.
which equations are you using?
Um, uh, in the first step, we are only constructing a neural network. We are only initializing some weights, and then these weights create an intermediate output. Then
How
intermediate
about
output.
what do you use for information? Do you use the equations or the data only?
The information I use data from initial or boundary conditions and other equations other than transport, such as like incompressibility or other equations that a problem needs.
I see. You use everything except. How about the initial and boundary conditions for the concentration? Are you using it there in that first step or
No,
not?
not yet. We use it for training the final output. So the whole process is trained end to end. We don't train the intermediate output.
Okay.
So the final output gives us a vector of three components. The first component is trained on the initial values of, as you said, concentrations.
Okay, thank you.
And in this slides, I'll go into the details of how I'm going to embed transport equation into the architecture. So first, to ensure the transport equation is inherently satisfied, we need to handle its mathematical structure effectively, meaning that in convection diffusion PDEs, the first derivative is always with respect to time. So we must treat time as an additional dimension when constructing our solution. And because of that, I introduced a new type of divergence operator that accounts for both the spatial and temporal dimensions. And in the next step, let's denote the intermediate vector as V, and which is generated by the neural network. And this vector does not yet satisfy the transport equation. And to enforce this constraint, in the first step, we construct a convection embedding tensor denoted by A from components of the vector V. So for clarity, the tensor A is showed in matrix form at the bottom right of the page to help illustrate how each component of vector V is arranged within tensor A. And the key feature of tensor A is its anti-symmetric property, which plays a crucial role because the row-wise divergence of A produces a divergence-free vector. You can verify it yourself by manually right now by taking the divergence, and the anti-symmetric structure guarantees that the divergence cancels out perfectly. I've also created a slide that provides a detailed mathematical proof of this concept, and to keep the discussion concise, I'll skip the details for now. So after constructing a divergence-free vector, we now introduce the diffusion embedding tensor, and we show how it combined with the convection embedding tensor forms a final vector that inherently satisfies the transport equation. Now let's begin with the first component of vector t, which we'll denote as t naught. Using t naught, we construct the diffusion embedding tensor d as shown in the equation. And tensor D is a diagonal tensor with only T naught as its diagonal component. And the structure of D is important because diffusion, unlike convection, acts isotropically in all spatial dimensions. And by representing it as a diagonal tensor, we ensure that the diffusion terms align with the transport equation's requirements. And the next, we calculate the divergence, the row-wise divergence of D. And after computing the divergence, we scale the results by gamma, which is the diffusion coefficient in the transport equation. And we form a vector R. And it's important to exclude the first component of R and put it 0 because diffusion does not depend on time in the transport equation. As you may recall, the new divergence operator incorporates time as a dimension. So now we construct the vector m as m equals t plus r, and we prove that m satisfies transport equation. To demonstrate that, set the first component of m as m naught equals c, and other components, remaining components of m as mi equals c times ui, where ui are the velocity components in each spatial directions. Now, if we take the divergence of m, we would have partial c over partial t plus partial c times ui over partial xi. This is the divergence definition of our divergence. And on the right-hand side, we should have divergence of t plus divergence of r. As we discussed, t is divergence free, so it's equal to 0, and divergence of r is calculated as it is. The first component is 0, and the other components will be used in the divergence. So we successfully proved that m which is the output of the embedding block, always respects the transport equation. We now test the efficiency of our method by testing it with Taylor-Green vortex problem. And Taylor-Green vortex, which many of you may know, is a fundamental model in fluid dynamics and is used to study turbulence and serves as a benchmark for numerical algorithms because of its ability to generate turbulence and complex chaotic flows. And the boundary conditions in this problem are periodic to ensure no artificial effects due to walls or inflow or outflow boundaries are present, which makes it ideal for studying intrinsic dynamics. The problem is set up in the following steps. First, an initial velocity field is defined in a periodic domain, as shown in bottom right of the page. And typically, it's a sinusoidal velocity profile. And as time progresses, the flow destabilizes, and which is due to the nonlinear interactions in the Navier-Stokes equation. And the small scale structures form, and leading to turbulence and energy dissipation. To set up the experiment, we need to address the governing equations for this problem, which is incompressible Navier-Stokes equations. And to reformulate it into a transport equation format, we take the curl of both sides of the Navier-Stokes equations. And this transformation introduces a new variable called omega, which represents the vorticity field. So after taking the curve, we arrive at vorticity transport equation, and we non-dimensionalize the equation to only have Reynolds number as a independent parameters. So in this case, the initial velocity field that we introduced to the problem would result in an analytical solution, which is shown uh, as uxyt, which shows that the solution decays over time, and the decaying rate is proportionate to Reynolds number. So we need to construct neural models in this step. We will construct two models. The first one will be vanilla PINN or standard physics-informed neural model without embedding any constraint. And the next one is our proposed neural network, which I will call TEN, Transport Embedded Neural Network. In the first step, it's essential to account for periodic conditions of the problem. And there are two main approaches to achieve this. The first one is to use prior knowledge, which instead of directly using xi as the direction along which periodicity occurs, we represent it with sinusoidal functions. For example, sine of 2 times pi times xi over t and cosine of 2 times pi times xi over t. And other directions that are not periodic remain unchanged. And the second approach is incorporating periodicity as a loss function, which involves adding the difference between the values at the beginning and at the end of the periodic domain as a term in the loss function. And the model will minimize the difference during training to ensure periodicity. And obviously, the first method is clearly more advantageous since it avoids adding yet another loss function into the total loss and keeps the optimization process simpler. And in addition to that, this approach enforces periodicity in a more mathematically rigorous way. You see the periodic conditions imply that a solution function and all of its derivatives must be periodic. So prior knowledge naturally satisfies this requirement, whereas using additional loss terms for derivatives might be less effective. So I chose a prior knowledge method to deal with periodic conditions. And in the next step, we need to embed transport for one of the models. And the methodology was discussed in the previous slides. So To provide an overview of the loss functions, we first consider transport embedded neural network, or TEN, which includes three loss functions: the initial condition loss, the incompressibility loss, and the vorticity loss. In general form of transport equations, the scalar quantity, which was denoted as C in previous slides, is not dependent on the velocity field. So, however, in our experiment, there is a correlation between vorticity field, denoted as omega, and the velocity field denoted as u. So we need to incorporate that into the total loss as a loss function.
I have a question
And
here.
for the case of,
I have a
yes,
question. So you chose the 2D, but if you do a 3D, how would you deal with
yeah.
the stretching term of vorticity? Where would you put that?
I haven't done the experiment, but I would suppose each of the components will be treated as a loss function separately.
But there's no equation. I mean, because you will have all the advection part, but then you have this extra term. So how would you?
Yes.
How would the loss function look?
Yes, I understand your question. In this particular example that I used as the experiment, somehow the scalar quantity is related to velocity field, and you're right, it would cause complexity for higher dimensions. But in general, since concentration of a species is not dependent on the velocity field and is intrinsically scalar quantity, I wouldn't assume that there would be any problem.
Okay, so you're interested. You're not interested in solving the Navier-Stokes. You're interested in solving the transport only.
Yes, exactly.
Okay, thank you.
You're welcome. And the second model is Vanellope, and the loss functions for this model include the initial condition loss, the incompressibility loss, and the Navier-Stokes, since the Navier-Stokes equation here is not embedded into the network anymore, and we need to incorporate it as a loss function. So by incorporating these distinct sets of loss functions, we aim to compare the performance of the two neural models under experimental conditions. So, and we now present the results of the vorticity field over time. And specifically, we examine the performance of the vanilla pin in this slide in solving the vorticity transport equation for the Taylor-Green vortex. And the results for the two different Reynolds numbers are displayed. The one on the left is for Reynolds equals 100, and the one on the right is for the case of Reynolds equals 0.1. And each set of heat maps contains 3 rows. The first row is the predictions by Vanellope over time. The second row is the ground truth or analytical solution. And the third row is the norm of deviation between the predictions and analytical solutions. And as you can see for the high Reynolds number case, the ground truth shows observable vorticity decay over time, and the Vanellope, however, remains stuck at the initial conditions and fails to evolve. And for the case of low Reynolds number case, the ground truth exhibits faster vorticity decay. As you can see, in time equals 0.025. You can see that vorticity field is down to a magnitude of 10 to minus 8. So, which is due to a higher viscosity and dissipation rates. And nevertheless, the vanilla pin again fails to capture this behavior and remains static over time. And next, we evaluate the performance of our model 10 for moderate and high Reynolds numbers. And unlike the vanilla PINN, 10 successfully avoids static solutions for the scenario of low Reynolds numbers, um, where turbulence decays faster, the error decreases over time, and which is a promising result for a physics-informed model. However, there's a negative implication that the reduction in error over time might indicate that the model does not adequately capture the initial conditions, since the initial conditions are the only provided data in this case, and this shortfall might highlight a potential limitation in the network's ability to learn them accurately. And for the case of high Reynolds numbers, the behavior obviously differs. The error increases in time, and suggesting that the model struggles to maintain the accuracy as the system evolves. However, the network demonstrates overall better accuracy in learning the initial conditions. Sorry, something went wrong. Not sure what's going on. Do you still have my connection?
Yes, we do.
I'm sorry, something went wrong. I'm not sure what's going on. I hope this. If if it's okay, I don't use the slideshow and only narrate the
Yeah, it's
slides
okay.
like this. Is it okay?
Yeah, yeah.
So and sorry, and finally to analyze the behavior of the loss function over epochs during training. For the case of 10, obviously for the low Reynolds numbers, the rapid decay of the system and the presence of higher order derivatives in the embedding block poses significant challenges for training, and as a result, the training struggles to reduce the loss function even after a large number of epochs. And for the case of Vanellope, interestingly, the loss function is decreasing over epochs significantly. However, as we discussed earlier, this minimum represents a false minimum and a non-physical solution of the problem. So to sum up, our model successfully is successfully trained in the case of high Reynolds numbers, but in the case of low Reynolds numbers, it fails to accurately predict the results, and it's not a new challenge. There's been a suggestions of this challenge in the literature for the case of low Reynolds numbers, for instance, a flow over a cylinder for 2D for a 2D channel. And in voltammetry or sensor applications, convection usually plays a dominant role. So it's somehow equivalent um, to the case of high Reynolds numbers. So we can spare the difficulties of the 10 model, and it can be used for the applications in voltammetry and sensor. It remains an excellent alternative for addressing multiphysics problems since, as Dr. Karnedakis mentioned, in this problem, the scalar quantity was not an independent parameter. It depended on velocity. However, in the case of a for example, transport of an ink inside a flow of water. The concentration of ink is physically independent of the velocity field. So for the case of multiphysics problems where where concentration of the species is also important, the PINN model could be an excellent alternative. And in future works, we could explore alternative methods which I described in the related studies to improve the PINN accuracy. Thank you very much again. I really appreciate the opportunity. If there's any questions.
Thank you so much for your talk. Now we open the floor for questions. Do we have any questions for the speaker from the audience?
Hi, Nazneen. Hi, Amir. I actually have a question.
Can you
Um,
introduce
Hi.
yourself first?
my name is Aditi, and I'm a second year PhD student working with Professor George. So
Yes, nice to meet you.
nice to meet you as well. Great talk. Could you please go on slide 16?
Yes.
Yeah. Can you explain for Rj the delta I that you have? Is it Kronecker delta or just a small perturbation?
What do you mean by chronicle delta?
Kronecker delta, like
Oh, you mean this delta right here?
the one
Yes, it's
below
chronicle delta.
when
Yes,
you
yes.
define Rj.
I haven't used chronicle delta here. I'm
Yeah,
not sure where you, what
what does it
equation
say?
you're referring to.
So in Rj, you write delta
Yes,
I Dij.
yes, yes.
So the subs
No, it's not
delta
delta. It's partial.
Partial.
partial. Okay,
It's
sorry.
partial.
Yeah, sorry.
Yes. No problem. No problem.
That's the diffusion term.
Do we have any other questions?
Hi, I have a question. It's Kyle here. I'm also a student working with George. So, I wonder, if I understand correctly, this method is very specific to the transport equation, right? Is there
Yes.
any way to use this method for other equations, like imposing a hard constraint for the neural net to satisfy other equations, or this is just a very specific architecture for the transport equation?
I've actually searched for that when I was writing the code for implementing the algorithm, and I was also looking for other equations in not only fluid dynamics in other parts of physics, but the only type of the equation that I could use this method on was the transport equation, and I'm not sure if you encountered other equations, it could be a great alternative for using it in physics-informed models.
Yes, thank you very much.
Well, Kyle is doing the
Sure, you're
Maxwell.
welcome.
Kyle is doing the Maxwell equation, so there's basically lots of convective components there in different species. So
Sorry, I couldn't hear you right. You said micro?
the Maxwell equation, the electromagnetic.
Maxwell.
Maxwell equations.
Yes.
Maxwell equations, there are four equations in Maxwell Faraday equations, as I recall, but I don't know if I could categorize them into a kind of transport equations. I will look into it after the meeting, but since magnetohydrodynamic is also a field I study sometimes, but I haven't encountered that kind of equation.
Do we have any other questions?
Hey, Amir, this is Raj. I have one question. I'm Raj. I work with
Hi.
Professor Dakis, and So if I got it correctly, so that means you're imposing the divergence-free condition, right?
Yes, yes.
So why don't you predict curl and divergence of curl is always 0?
Divergence of which parameter you said?
Curl, the rotational, the curl vector.
That's equivalent of using divergence-free formulations, which use a stream function. I've actually used all of the methods I discussed in this slide for solving the transport equation. Still, okay. I used sequence-to-sequence learning, curriculum learning, and stream function formulations for solving the vorticity transport experiment that I discussed, but none of them were successful. And only the embedding of transport equation showed promising results.
Yeah, because there is a paper where I can say put it there where you can impose this kind of condition as a hard constraint. Suppose for you want to predict the divergence free, so you can just predict a function of which you
Sure,
can
yes, yes, yes,
you can take
sure.
the curl and
So,
just
but
impose that divergence of curl is 0. So that will be a very straightforward.
you need to keep that in mind. If you somehow embed divergence-free constraint or incompressibility constraint into the network, you wouldn't be able to eliminate the loss function relating to Navier-Stokes equations. So the main equation that is somehow troublesome in this problem is actually the Navier-Stokes equation and not divergence incompressibility. Actually, when I was coding the experiment, I encountered that the loss of divergence decreased very quickly to a magnitude of um, 10 to minus 4 after a very few epochs of training.
Okay. Thanks.
You're
Amir,
welcome.
we're working on bioreactors. So Chansi, I don't know if Chansi or Juan are still here, but they solve these equations, but they have a kind of staggering method. They start with Navier-Stokes for a while, and then they turn on the transport equation. Chansi, are you
Yes.
still?
Yes.
Can you tell Amir how you do it?
Yes, so we train the Navier-Stokes equation for a while and use the velocity information for the diffusion reaction system.
Yeah. The kinds of equations that are used in bioreactors I'm familiar with also include reaction um, type of mechanism inside their PDs. So it could still be manipulated to somehow use this method in order to solve those equations, but it needs to be checked.
Okay. Do we have any other questions, comments?
No, thank you, Amir. Thank you for coming today.
Thank you so much, Doctor, for this opportunity. Thank you very much.
Thank you so much, Amir. I think Raj put the paper in the chat, if you can see.
Yes.
Okay. So I think it's time to close the session. Thank you for joining us today, and thank you everybody for being here on Black
Thank you so much.
Friday. Yeah, I hope everybody has a great weekend ahead. Bye.
Bye, everyone.